But the most important term is XX transpose, which is computed by calculating this inner product of the tilde vectors mentioned in the previous slide. So the covariance matrix of the mean subtracted data looks like this matrix shown in equation 1. Now, the off-diagonal terms are the ones that tell you the variability between the dimensions. So if these terms are large, that means there is greater amount of variability. The optimal representation of the data, the one that we are searching for, should be such that the off-diagonal terms of the covariance matrix must be 0. Because we want to reduce the intervariability between dimensions as much as possible. Because if they are very much interrelated, then that's just redundant data, redundant information that we can very well discard. Further, we need to retain those dimensions that present us with the greatest variability, which means the diagonal entries of the covariance matrix of the data in the appropriate space should be such that these entries are very large. Large variability means a lot of information. So that's what we are aiming for. And to achieve that, we need to transform the data into an appropriate space. Let's call that new representation Y and the old representation, that of the data matrix X. So we are looking for a transformation matrix, which is a change of basis matrix P, which takes the data from X to Y. At the same time achieving the properties that I just mentioned in the previous slide. So P is what we need to find. We don't know what P is, but let's say P comprises of all these row vectors, P sub 1 stacked up on top of each other, where each row forms the new basis, and I call the principal components, for a reason that will become clear in the next few slides. So how do we find the change of basis matrix P is the quintessential question. Remember what we are shooting for. We are shooting for the covariance matrix of the transformed data space, CY, which is such that it maximizes the diagonal entries of CY, such that it gives us the most amount of information, and it minimizes the off-diagonal entries, so that it should be more diagonal looking as possible. So what does all that above mean? It means that P should be such that CY is diagonal, where CY is the covariance matrix of the transformed space. Okay? And since the columns of P must now form the new basis, we must have that P is an orthonormal matrix, that is PP transpose is I, which means P is its own inverse. So mathematically, that means that we have a transformed representation Y, from which we can construct a covariance matrix denoted by C sub Y. But the transformation Y can be written as Px, so we just substitute Y equals Px. And Px whole transpose means X transpose P transpose, so we just rewrite those terms. And that means that Cy can be written in the form, the scalar multiple 1 over n minus 1 times P times XX transpose times P transpose. Or simply speaking, P times S times P transpose, where S is the symmetric positive definite matrix defined as 1 over n minus 1 XX transpose, right? The covariance matrix of our original representation. Now, because this is a symmetric positive definite matrix, it's a square matrix, it is diagonalizable. So S can be written in the diagonalizable form ED transpose, where E is now a new M cross M orthonormal matrix whose columns are eigenvectors of S, or the covariance matrix C sub X. And D is a diagonal matrix whose diagonal entries are the respective eigenvalues of S. Okay, so in a sense, we have got C sub Y as P times ED transpose times P transpose. And we want, our objective is to make CY diagonal, right? So if we choose P to be E transpose from the orthonormality of E, it turns out that CY is diagonal. So our choice of P, the change of basis matrix, should be E transpose where E is just the columns of the eigenvectors of S. Okay, so that is how we must choose the linear transformation and the change of basis matrix. And once we have that, once we have the diagonal form, we will choose the top, let's say, J diagonal eigenvalues, because that gives us the most amount of information about X, and we can annihilate the remaining eigenvalues as long as they are minimal, orders of magnitudes lesser than the other eigenvalues that we want to retain. And that's how we can achieve compression of data. So one question remains though. I mean, E is formed by the eigenvectors of S. So how do we find the eigenvalues and eigenvectors of S? Well, you could do it by hand if the problem is very small, but if the problem is small, we wouldn't require all this. Often is the case the matrix, the data matrix is of large dimensions, so we cannot resort to hand, and we have to use computational technique. And one of the techniques that becomes very useful in computing eigenvalues of large data matrices is the singular value decomposition, which you will learn to employ in the lab class in more detail. So we will do that. We'll actually implement this principal component analysis technique to a data compression example, which will give you a much better idea about the mechanics of performing principal component analysis. Of course, once you have the transformed representation, you can recover the original data by inverting the matrix P, and it turns out the invertible matrix is a matrix V, which is P transpose, which we already mentioned earlier. So with that, we will conclude our lecture on principal component analysis, and we will actually solve a numerical problem using a computer, because that's the whole point, in the lab class. Until then, take care.